So today we're going to talk about modeling and optimization. Okay, this is sort of an introduction to how do you find the highest of something and how do you find the lowest of something. We've already done this a little bit by graphing and trying to find the highest point in the graph and the lowest point in the graph, but this is now the question of how do we apply this to real life situations. So we'll walk through a couple of introductory cases and then I will go through the process for optimizing, for writing the equation, for solving it, and then coming up with a reasonable solution. Now, I don't have my graphing calculator at home. It's in my office at work, so we'll make our best guess using Desmos or some other modeling activity. So this is a story about two print shops, right? You go to a print shop, you need something printed. There's an initial fee. You still call it a typeset fee, even though you're not actually typesetting inside of a big machine. You're processing it through a computer and taking the initial information. So this one print shop charges a $5 initial fee plus 50 cents per business card. The other one charges $8 up front and then a quarter per business card. So the first one charges you less initially but more per business card. The second charges more up front but less per card. So you would figure that if you only had a couple of cards to print, you'd go with the first one. If you had a lot of cards to print, you'd go with the second one. But where is that crossover point? So let's try to set up an equation. So for each of these, we're going to have the cost as the fee, right? We'll call it the initial fee plus cost per card. All right, so for set A, the typeset fee is $5 plus 50 cents per card. The second one is going to be $8 plus 25 cents per card. When will they be equal to each other? Well, we got a couple of options. One of them is if we want the cost to be the same, where will the cost for part A be the same as the cost for shop B? Well, that'll happen when 5 plus 0.5c equals 8 plus 0.25c. All right. We solve by moving the 5 over to both sides here. I'm going to do two things at once. I'm going to subtract a 5 from both sides, and I'm going to subtract the 25 cents for business card for both sides. Make sure that you're lining up like items, right? So 5 and minus 5 gives you 0. The pieces that have the variable, the 50 cents minus 25 cents gives me 25 cents per card, and 8 minus 5 is 3. Those zero out as well. Okay, dividing by 0.25 is the same thing as multiplying by 4. So we get 12. So 12 business cards is where they're the same. If you have fewer than 12 cards, then go with these guys because they'll charge less up front. If you have more than 12, go with that one. And if you have exactly 12 cards, then, I don't know, go with the one that's closest to your house and has better hours. All right, let's try graphing this. All right, so I'm going to pull up Desmos, and we got two equations here, right? We got y equals 5 plus 0.5. I'll use x because Desmos likes that. And then I'll do y equals 8 plus 0.25x. Now, you can see that this is a lousy window to graph on because it only includes a couple of cards, and it includes the negatives, right? I'm not going to have negative numbers of cards or negative numbers of dollars. So let me move it down here and zoom out a little bit. All right, so now you can see when x is 12 over here, then that's when the two costs are the same. The blue line is the second company that charges more up front but less per card. The red line is company A that charges less up front but more per card. So if you have more than 12 business cards, you can see that you're going to end up with more costs for A, so you would want to go with company B because they're less expensive, right? We're trying to use less costs in this case. All right, so that's one example. This example is similar, right? Sending a package by two different companies, an initial price plus a cost per ounce. So one of them charges more up front but less per ounce. The other charges less up front but more per ounce. If it was a reverse, like if one company charged more up front and more per ounce, then right away the problem's done because they're the more expensive one. All right, so let's set this up. I'm not going to solve the whole thing, but the first one, they call it Fast Fellows and Speedy Service. So Fast Fellows charges $3.50 plus a quarter per ounce. Speedy Service charges $4.75 plus 10 cents per ounce. Okay, so if you want to find out where they're the same, set them equal to each other. Obviously, if you're only sending a small package, the first company will be more efficient. If you're sending larger packages, the second one will be better. But what's the crossover point? That's the issue at hand. All right, this one goes back to the days when you used to rent DVDs out of a DVD box, but the premise at least other situations too. So the idea is if they charge $2 for a 1-day rental, on average they're going to rent 200 DVDs from the machine. Now, if they raise their price, they'll make more money, but fewer people will buy them. For a while, they'll actually start making more money as they raise the price up, but then they're going to raise the price to a point where not enough people are buying them anymore, that no matter how much you charge, people just aren't going to buy them, and you'll start losing money. Okay? So the question is, what should they charge to maximize their income? Well, first of all, how do we calculate their income? Their income is the cost per DVD times the number of DVDs that they rent. So right now, they're charging $2 a day for 200 DVDs. So they're pulling in about $400 a day. This says that if they raise them by 10 cents, then they're going to lose 5 DVDs per day. Okay, so the cost of each DVD will start at 2, and they'll add 10 cents per price increase. So that's what X is in this case. X is the number of price increases. Hey, how many DVDs are they going to sell? Well, they're going to start at 200, and then they're going to lose 5 DVDs for each price increase. All right, so they start at $2 plus 10 cents for each price increase. The number of DVDs goes down. All right, so let's distribute this. 2 times 200 is 400 minus 10x plus 20x minus 0.5x squared, right? 0.1x times 5x, 0.5x squared. Right, you want to clean this up a little bit, you can make it y equals negative 0.5x squared plus 10x, right? 20 minus 10 is 10, plus 400. All right, so now we've got to graph this. Now, if you got a graphing calculator, that's the best option because you can use that second in calc, go to find the max, left bound, right bound, and it'll give you the number. I don't have a graphing calculator at home, so I'm going to graph this on Desmos and see how close I can get it. So the equation was y equals negative 0.5x squared plus 10x plus 400, right? Let's double check. 10x plus 400. Okay, so on this window here, I don't see a whole lot. I'm going to have to zoom out quite a bit so that I can see the maximum. Remember, we're starting at $400. So maybe a reasonable window would be to let my x's go from 0 to 50 and let the y's go from 0 to 450. All right, so we can do that here, right? The x's go from 0 to 50, and the y's go from 0 to 450. Let's make it 460. Good to see the top of it. All right, so where does it peak? It looks like it peaks right around here, okay, at 10, 450. So it looks like if I raise the price 10 times, that will be the maximum of my income. Because you notice if you raise the price, even though you're selling fewer DVDs, you're actually pulling in more money, right? Instead of 400, now you're up to 450. Once you pass that 10 mark, then it starts going down, down, down until a point where if you raise the price 40 times, you run out of customers, right? Down to 0. All right, so I'm going to go with 10,450. What does that mean? Well, we figured out that the max happened at x equals 10. 10 is the number of price increases. So I'm doing 10 price increases of 10 cents each, which means I should raise the price by $1. Right, so if it was $2 and I raised the price by $1, my new cost is $3. You can double check your work. If I rent it for $3 and I sell 150 DVDs, right? 200 minus 5 times the 10 price increases is 150. So 3 times 150 is $450. So that's the cost per DVD, and that's how much income I'm going to make. If I raise the price any more than $3, it's going to start going down again. Okay? So what we just did, whether we recognize it or not, is called an optimization problem. Optimization means you either want the biggest of something or you want the smallest of something. In this case, we wanted the biggest of something. We wanted to maximize the income. So we wanted to set an equation for the income based on number of price increases and solve the equation to find where the highest point is. Okay? You don't always want to maximize things, right? If you're trying to find the cost of something and you're trying to manufacture an item, you would not want the highest cost to manufacture it. You would try to keep the costs as low as possible. Right? So in this case, we're trying to maximize. Other times, we're trying to minimize. Right, so this is just a list of how to solve optimization problems. You're going to carry these same concepts, by the way, into calculus, except you're going to use derivatives to find the maxes and mins rather than graphing it. But the concept and the setup of these problems is actually pretty similar between the two courses. So learning this now will not only help you in this course, it'll help you in calc as well. So the first thing is read the problem carefully, figure out the difference between constants and variables. So if it tells you that this piece of paper is a certain size, and that size remains the whole problem, then that's a constant. Nothing's changing. Decide what's being maximized or minimized. So in our last example, it was the income that was being maximized, and so that's what gets the dependent variable. So the income was based on how many times we raised the prices. And then we want to write the function as a quantity as a function of one variable. We did that pretty easily in our problem, but sometimes you're going to have to do a little substitution back and forth. So in our case, we were able to write the cost or the income as a function of how many times I raised the price. Determine an appropriate domain. I kind of did that when I looked at my graph and I said, well, I'm not going to need negative dollars for income, and I'm not going to run a negative number of DVDs, so I'm only going to consider positive values, and then I adjusted my window to fit those values. Okay, graph the equation, find maxes and mins, and yes, you're going to have to adjust your viewing window on a lot of these because they're real-life problems. So real-life problems don't always happen between negative 10 and 10 on a graphing calculator. And then it says keep the domain in mind as well. You're going to want to make sure that you don't have like negative volumes for your box or negative incomes for your business. And then the last thing says make sure you answer the question that was being asked. So when we finished up our problem here and we said, well, it's at 10, 450. That's our answer. But the answer wasn't 10. 10 was the number of price increases. But the question actually said, what should they charge? So we had to take that value that we found, substitute it back in to find out what the new price would be. So in our case, it was 10 price increases of 10 cents each, means raise the price by $1. So our new cost is $3 instead of $2. All right, so a couple of the classic problems here. Says a yard is to be enclosed with one side along a building, so it only requires 3 sides of fencing. What is the largest area you can enclose with 1,200 feet of fencing? So let's take a look at what a diagram of this situation looks like. This is the building. I'm assuming my fence is rectangular, which when you do these problems is a good guess. So I've got one side of fence here, a side of fence here, side of fence there. Okay. I'll call these two things the same because in a rectangle, the two sides opposite there are the same. That's my third side. All right, first of all, I'm trying to maximize something because it says largest. Maximize what? Maximize the area. So for this, we're going to reach back into our geometry knowledge from probably high school is the last time you saw this kind of geometry. Area of a rectangle is length times width. So area of a rectangle, in this case, is x times y. That's our primary equation. There are other things that will fit into that equation, but one of the key things is to start with your primary equation, make everything else fit into that. So in this case, we're trying to find largest area, so we're maximizing area based on the two dimensions that we're given. All right, so now I got three variables. That doesn't look very appealing. There's one thing I haven't used yet, and that is the 1,200 feet of fencing. If I add up x plus y plus x, that adds up to 1,200. So remember I said there were some things that were constants and some things that were variables? 1,200 is a constant. I've got 1,200 feet of fencing. It just depends on where I put it, but it remains 1,200 feet of fencing. Right, so if I subtract the 2x from both sides, right, because x plus x is 2x, I get y equals 1,200 minus 2x, which means I can replace the y over here with a 1,200 minus 2x. That x carries down. So now I have everything in terms of one variable. All right, what values would make sense for x? Something bigger than 0. Otherwise, your fence is going to be flat against the building. And something smaller than 600. Because at 600, all you would do is you would walk 600 feet down. Then you'd turn around immediately and walk another 600 feet up. And you wouldn't have any area in that fence either, right? So somewhere between 0 and 600 are reasonable values for x. Okay, with the two extremes being at the endpoints of not having any area at all. All right, distribute, and I end up with a negative 2x squared plus 1,200x. All right, I got a couple options for this. Actually, I could, if you remember stuff about parabolas, that negative b over 2a, you could actually use that in this case. But if you haven't gotten that far, let's graph this. So negative 2x squared plus 1,200x. Negative 2x squared plus 1,200x. Now, obviously, we're going to need a better window than this. Because we're talking area, the area could be pretty large. So, one of the nice things about Desmos is you can just keep zooming out until you get something that looks reasonably like a graph. Yeah, that's a big graph. So let's keep the y's where they are, but look at the x's. The x's aren't going to go anywhere above 1,000. So if I click the little wrench, let's make the x's go not to 30,000, but to 600. And we'll start the y's, and we'll start the left side at 0. Ah, okay. There's a little bit better graph. If I want to find the maximum, look right there's the maximum. 300 and 180,000. Okay, so you could draw yourself your graph. You can plot the highest point. Highest point is 300 and 180,000. So as an ordered pair, x is 300, y is 180,000. Well, here's my answer. That's the area. The 300 goes with the x. So what I'm saying is I have 300 here. I should put 300 here. And if that's 600, the other 600 go down there. So I have a 300 by 600 plot of land, 1,200 feet of fencing, and the maximum area that it can enclose is 180,000. If I use other dimensions, as you can see from the graph, if I make x too small, the area will be too small. If I make it too big, the area is going to be small again, right? It's going to, instead of it going long ways like this, it's going to get shorter top to bottom versus shorter left to right. Yes, I realize you can't see me making motions with my hands, but rather than going very narrow like this, after a while it'll just go very narrow like that. All right, let's try another one. This says you got a 5,000 square foot yard. What's the least amount of fencing you can use? So again, I'm assuming some sort of a rectangular setup for this fence. This time, it's not bordered by any kind of a wall. So I need all four sides for my fence. Okay. The area is 5,000. Now it says 5,000 square feet, but that doesn't guarantee that it's a square. Any kind of area is measured in square feet, even if it's circular. What am I trying to do? I'm trying to minimize something. Because it says least amount of fencing, so I'm trying to minimize perimeter. Well, again, let's call the sides x and y. Just remember that the figure has 4 sides. So 2 of them are x's, 2 of them are y's. So that's the perimeter that I'm trying to minimize. Again, I'm left with 3 variables in here. I'm going to need to replace one of those independent variables, either the x or the y, with a function in terms of the other one so that I can solve it more easily. How do I do that? Well, there's one piece of information I haven't used yet. Right? If you get to the point where you're not quite sure where to look for the information you haven't used yet. So in this case, the information I haven't used yet is that the area is 5,000. So I calculate area by doing length times width. If the area is 5,000, then 5,000 equals xy. Divide both sides by x. So I get an equation that says y is equal to 5,000 divided by x. And now I can replace this y with a 5,000 divided by x. All right, so my perimeter is going to be 2x plus 10,000 over x. A funny looking equation, but something we can graph. So I got 2x plus 10,000 over x. So now I've written the perimeter entirely in terms of one variable. So let's try it. We said y equals 2x plus 10,000 over x. And we end up with a graph that doesn't show us much. So in this case, it could be that we have a lousy window. If I'm looking for a minimum, I'm hoping that this graph goes up again somewhere. So if I come out a little bit, nope, doesn't seem to be going back up again. So let's zoom in on a portion in the middle here. So maybe let's go with the x's from 0 to 300. And the y's, let's go from 0 to 2,000. Oh, okay. So by having such a massive window, that's what I was missing. Because my window was going up to like 20,000, 30,000, 40,000. Look at it now that I changed it. So it probably doesn't even need to go up quite that high, right? So maybe let the y's go up to 1,000. Okay, and let the x's go up to 200. And now I can start to see where this thing bottoms out. This one's a little bit harder to see. This one, you might want your graphing calculator to help you to figure this out, to see exactly where the low point is. It's got to be somewhere between there and there. It would strike me that it's got to be somewhere around 80, maybe even 70. How about right there? Okay, so if I drag it over, it kind of gives me an idea that 70.711 is the minimum. Let's see if that's reasonable. All right, again, I would do this on your graphing calculator if you have one at home, because you're going to get a more accurate answer than I am by eyeballing it. I could go through and take the derivative just to verify. Well, let's try it like this. So if we say x is equal to 70.711, then what is y? Well, the blue equation tells us that y is 5,000 over x. All right. I can grab a regular calculator and divide those out. Yep, and I get 70.71 for the other one. Turns out this thing is a square. Not everyone will work out to be a square, but this one is. So if the question says what is the least amount of fencing, you've got 4 sides that are each 70.71 units. So when you multiply that out, let's see what you get. 282.84. So that's the least amount of fencing that you need to enclose a 5,000 square foot yard. Right? Anything less than that, and you won't have enclosed the whole yard. Anything more, and you're using more fencing than you need. So it turns out that the answer really is a square that is enclosed by about 283 feet of fencing. All right, this one here is sort of one of the classics of max-min problems. I wish I had my boxes with me to show you, but you can actually do this. You can take a piece of paper, right? In this case, a 16 by 21 piece of paper, but an 8.5 by 11 will do. A 5 by 8 will do. Doesn't have to be a specific size. So you can take a piece of paper and you can cut out the corners. Right, so you cut out the corners here, here. Each of these corners that you cut out are going to be squares. And so you're going to be left with the base of the box that looks like this. Right, that's your base. And then these little things here, those things are your flaps. Right, there's one here, there's one here, there's one here, and there's one here. Essentially, those flaps become the sides of your box. So you got a side, a side, a side, a side. Fold those up. The squares you cut and you put in the pile, put in the garbage, whatever, you don't keep them. The other four sides you fold up, and you got yourself a box. Now, the question is, how big of a square do you cut? If you cut too small of a square, you're going to have a very shallow box with a big base. If you cut too far in, you're going to have a very tall box, but the base isn't going to be very big. So the question is, where do we fold those sides to make the highest possible volume for the box? All right, so the sides were 16 by 21. I'm going to call the side of my square x, which means that every side of these squares are x, right? Because they're squares. And I want to cut out squares of the same size. Otherwise, my sides of my box are going to be taller on one side than the other, and that doesn't make any sense. So what do the base of my box look like? Well, if this piece is x, that piece is x, and the whole side is 16, then this thing here is 16 minus 2x. The other side here is going to be 21 minus 2x, right? Because it's the whole side of 21 from top to bottom minus this piece up here minus that piece down there. All right, so the volume of a box is length times width times height. So volume equals length times width times height. Now, we can talk about appropriate domains. If you look at the 21 minus 2x, you never want 21 minus 2x to be less than 0. You always want it to be greater than 0. So to do that, you want x to be less than 10.5. But wait, there's a side up on the top, right? That's 16 minus 2x. You don't want that length to be negative either. Okay, so a little quick solution here. Divide both sides by a negative, changes the sign. You want x to be less than 8. So for the domain, you go with the more restrictive of them. So for the domain, you'll take x values between 0 and 8. Once you get past 8, then that one side of the box has a negative value. And if you graph it, it'll continue graphing past 8 because it doesn't know that it's associated with a box. All right, we could simplify this if we want. Actually, we could put it in Desmos just like this, right? We could just put it in as the 3 factors. Or you can distribute it and simplify it. Here, I'm just going to put it in the way it is. So I've got (16 minus 2x, 21 minus 2x, and x. All right. And if I graph it on the window that I'm given, I don't see very much. Oh, I lost an x, that's why. So let's play around with possibilities here. Let's say at first I decide I wanted the x's to go from 0 to 20. What does this graph do? It actually goes down and then back up again. Well, anything past 8 doesn't help us because you notice that down here this volume is actually negative, and then past 10.5 the volume is positive because we're multiplying two negative sides together. Let's not do that. All right, so let's make the x's go from 0 to 8. And let's make the y's. We don't need negative y's, right? No negative volume. And then for the max, looks by 500 it probably hits the max. All right. This graph looks almost like a parabola, but it's not strictly parabolic because it's not symmetric. Where's our max? Again, on a graphing calculator, you might have it a little bit easier. Second in calc, go to find the intersection points. It looks to me like that's the max up there, just eyeballing it. I could go through and take derivatives and stuff, but having done this problem before, I'm rather convinced that that's the maximum. So 3, 450 is the max. What does that mean? So the maximum point is 3, 450. 3 is your x value. That's the size of the square that you should cut out. That 450 is the volume that's produced by that box, right? So 16 minus 2 times 3 is 6. So one side of your box would be 10. 21 minus 6 is 15. And we said that this was 3. So 10 times 15 times 3 gives you 450 for a volume. Now, I got so excited about the problem that I never actually looked at the question. Maybe that's because I wrote it. I know what it says. So it says an open box with a rectangular base is going to be constructed from a rectangular piece of cardboard 16 by 21 by cutting a square from each corner and then bending up the sides. Find the size of the corner square that will produce a box having the largest possible volume. Disregard the thickness of the cardboard. Okay, so the only thing we need for the answer is that the size of the corner square should be a 3-inch square. So cut 3 inches by 3 inches off there, and you'll have the box that produces the maximum volume. All right, I'm going to separate this into a second video. I got a couple of more examples, but I will do that in part 2.